Hello guys, good morning. So I'm back. Sir DB is here to discuss to you some basic principles on linear systems. So for linear systems, we mean that the equations involved are raised into a power of 1. No? So the consistency of the variables are actually in the first order degree, and the a normal situation is that the number of equations uh, is equal to the number of unknowns. So if we consider a system of equation in an upper triangular form, meaning to say that if we look at this system of equation, we actually form an upper triangle, and basically this upper triangular system is easily solved by simply starting from the last equation. Okay, so we can easily solve the value of the last unknown x3 using the third equation here, such that your x3 will simply be equal to 5. And upon doing so, we simply back substitute this value of x3 from the third equation going down to the first equation, and it will also give us a very easy procedure on how to find the rest of the unknowns, wherein x2 is simply uh, solved, and the value of -1 is obtained from equation 2, and x1 consequently or subsequently is also determined by simply back substituting the value of x2 and x3 in equation 1. So take note that the first objective of elimination method is simply to convert the matrix of the system into an upper triangular form, so that the last equation will consist only of one unknown, and by proceeding with back substitution, the rest of the unknowns will be obtained. So to give you a detailed procedure on how the triangularization or the transformation from a matrix of a linear system to a triangular form is made, so we consider example 1.1, considering 3 equations 1, 2, and 3, and we ought to convert the system of these equations into an upper triangular form. So it will involve 1 or 2 cycles actually. Since your number of equations is 3, we have to reduce the coefficient of the second and the third, such that the form of the equation will actually be similar to this triangular upper triangular system that we consider here in this presentation. So the first cycle will involve the elimination of the variable x1 first, by simply taking note of the first and second equation. So what we do here is we simply multiply the first equation by 3 and the second equation by 4, okay, and add them to eliminate x1. So these are now the multipliers that I placed. Of course, we have to um, operate on the whole equation such that the left hand side and the right hand side will actually be multiplied by 3, and so with this equation 2. And upon adding, taking note that your x1 coefficient has the value of a positive and a negative number, then by simply adding it after multiplying it with this coefficient, we take note that the x1 here will become 0. Hence, it will be eliminated. So with such elimination, we actually reduce the form of the second equation into this resulting equation. So upon multiplying now equation 1 again by -1 and equation 3 by 4 and adding them, it will now eliminate the value of x1 on the third equation. So this will represent our new equation for equation 2. Okay, so this is the new equation 2, and this will represent the new equation 3. Okay, such that the first equation will be retained, while the second and third equation will actually be updated into these equations, new equations 2 and new equation 3. Okay, so that involves now our first cycle of elimination. So since we still need to reduce, okay, one term to 0 here in the third equation, we need second cycle in order to eliminate x2. So it's a correction, in order to eliminate x2 in the third equation. Okay, so remember that here in the first cycle we ought to eliminate x1 in the first and the second, while here we only need to eliminate x2 in the third equation, since we only have 3 equations here in this example. So by simply multiplying equation 2 by 2 and equation 3 by -10, then adding it to eliminate x2 in the equation. So we therefore use, okay, so these two multipliers, 2 and -10. So the reason for a negative sign here is to make the signs of x2 here the negative of each other. Okay, so because if we add it, we need to cancel it out. Therefore, a negative sign must be placed either on this first multiplier or the second multiplier. In this case, I opted to place the negative sign here at the second multiplier, and adding it will yield my new equation 3. Okay, so the entirely new system of equation now, which is in the upper triangular form, is shown below. So we have reduced now our system of equation in an upper triangular system, and using the logic previously by easily obtaining the value of the last unknown x3 and back substituting, we now yield x3 is equal to 3, x2 is equal to -2, and x1 is equal to 2. So doing the same procedure in terms of the matrix operation will give you a more systematic, okay? So the purpose of using a matrix operation is to give you a more systematic way for us to easily convert it into a program later. Okay, so the system of equation now, which involves 3 equations and of course a right hand side which is a vector of constants or coefficient, can be written in this form. So you call this now an augmented matrix, where A is actually the original matrix of coefficient, okay? While B here is the vector of constants, okay? Okay, so this is written with a vertical bar here, but we can omit it, so we can make a vertical bar or a dash, okay, in order to separate the coefficient matrix into the vector of constants, or we can also ignore it, okay, knowing that the last column here simply are the augmented, simply augments the original matrix by the vector of constants. So the above expression is now known as the augmented matrix, and we then perform the elementary row transformation or operation to convert the matrix into an upper triangular system. Okay, so the first cycle is the same as what we have done a while ago. So we simply multiply, okay, your okay, we simply multiply your row, okay, so these are the rows in question, and the multiplier is actually given by the coefficient of the first row or the first equation, which is actually called a pivot, okay. So you multiply these equations, R2 is the equation, so this is the row 2, no, row 2 equation. We multiply the row equation by the pivot, okay, and then add it, okay, and then add it to the row equation of the pivot multiplied by the coefficient of the row in question, okay. So this is now row 2, the one that is in question here. So for a systematic procedure, we actually did exactly the same as what we have done here, okay. So we simply multiplied 4 times row 2, okay, and then add it to 3 times row 1, okay. So this is the, again, the pivot row. You call this now because this 4 here is actually your pivot, okay, and the pivot here will be multiplied to the row in question, okay. So this is R2, that's why this is a 4R2 plus 3R1, okay. Then you add it, you actually have performed the same, okay, procedure here in matrix form. And also, we do it on the second. So this is the pivot multiplied by the row in question plus, okay, so there's a negative value here, negative 1, R1 simply refers to the multiplier again. So if we take a look at the second step here, okay, so this is 4. Okay, 4 times the row in question, which is R3, and this is negative 1, R1. Still, you are here on the pivot row. Okay, and again, this is the row wherein your reduction or transformation is being performed. So this is the row in question. So 4 times R1, and then negative 1 times the pivot row. So we add it, okay? The reason for a negative sign there is because these are both positive. Again, we need to eliminate it. So we just put a negative value here, or we can also do the reverse by opting to put a negative sign here. Okay, so we now yield, upon performing this, we yield with this new, okay, set of augmented matrix. So take note that we zeroed the value. Okay, we zeroed the value. Our objective is to zero the value of the matrix under, okay, always under the pivot. And the pivot here is actually your 4. Okay, and the second cycle, what we do is we are concerned by with the zeroing in your negative 2 here by using this as your pivot. Okay, so your pivot now is negative 10 multiplied by the row in question plus the number below the pivot 2 multiplied by the pivot row. Okay, so those are the terms you need to be familiar with to easily discuss things when you go to programming. Okay, so what we did here, 2R2 minus 10R3, is exactly the same procedure we did here on our second cycle. Okay, so this is your 2R2, and this is the negative 10R3. Okay, so this is simply 2R2 negative 10R3. Okay, so we're just trying to convert the procedure in a more systematic way for us to convert it later with a program, because the procedure here above is a little bit in a human language, and we cannot expect machines and computers to understand them, so make it more systematic in this case. Okay, so by doing so, we actually finally made the triangular matrix for the upper. Okay, so again, we are concerned with the upper triangular form, okay, of the matrix. And by simple back substitution and knowing that your x3, the last unknown, is simply equal to the ratio of this number with that of this coefficient, then we get x3 equals 3. And back substituting, we get x2 equals negative 2 and x1 is equal to 2. Okay, so the above procedure uses what you call a elementary row transformation or operation. We can call it as a transformation or operation. So I intended to use more the word operation because transformation has a different meaning in matrix. So we have the ERO, and these are as follows. So the first ERO is we multiply any row of the augmented coefficient matrix by a constant in order for us to eliminate, okay, one variable or zeroing one variable below the pivot. So what we also did in the ERO above is we can add a multiple of one row to a multiple of any other row. And we can also interchange the order of any two rows. Actually, it's not used in the above example, but we need to do this later because sometimes we will be encountering pivot values, the diagonal values, which are zero values. Then, in order to avoid division by zero in your program, so we need to add an error procedure, okay, an error detecting procedure to at least remedy the situation when your diagonal pivots have values equal to zero. So for worthwhile notes here, so we have an alternative to converting an upper triangular form is to use a lower triangular form. Okay, so if you can do a reduction into an upper triangular form, we can also do a lower triangular form. Okay, so this is an upper triangular matrix. This is a lower triangular matrix. Okay, and using these two here, we'll come up to a method known as the LU decomposition. So we will be discussing that later. So there exists a possibility that the system has no solution if a zero value is encountered on the last diagonal. So we cannot do anything about it if that is the case. So if a zero is encountered on the diagonal, not the last diagonal, we cannot use the row to eliminate the coefficient below that zero element. Therefore, we need to use ERO number 3 in order to interchange the order of any two rows and avoid a misbehavior which will lead to errors in your program solutions. Thank you very much. So the next video I will be discussing to you a more systematic elimination procedure known as the Gaussian elimination. So thank you very much for listening, and I'll see you on the next video.